Hello everyone. So previously we had discussed on the topic tangents, strongly connected components algorithm, right? So now let's discuss on the Kosaraju's SCC, nothing but the strongly connected components algorithm. So this is also related to the strongly connected components itself, right? So see, let's get into the definition part here, right? So let's see what the definition part say here. So Kosaraju's algorithm is used to find all the strongly connected components in a directed graph. Again, Kosaraju's algorithm is used to find all the strongly connected components in a directed graph. A strongly connected component SCC is a maximal subset of vertices. Again, a strongly connected component SCC is a maximal subset of the vertices such that every vertex is reachable from every other vertex in that subset, right? So this is fine, I believe. A strongly connected component SCC is a maximal subset of the vertices such that every vertex is reachable from every other vertex in that subset. So previously also we had discussed this one. By this time you have to be knowing what are strongly connected components mainly. It's a maximum this one subset of the vertices or the maximal subset of the vertices such that every vertex is reachable from every other vertex in that particular subset, right? So, and one more thing, what it states initially, Kosaraju's algorithm is used to find all the strongly connected components, right, in a directed graph. We know the strongly connected components, right? Previously, we had discussed what are the strongly connected components within the graph. Basically, if it forms a cycle, then if the particular node is isolated, then it is said to be a strongly connected component. Yeah, we know this one, right? So now let's get into the explanation part. So first, so let's get into the first point here. Kosaraju's algorithm works in two main phases. Just remember this one. One is DFS and stack. The another one is transpose and DFS, right? So let's see the first one, DFS and the stack. So what we will be doing here, we will perform the DFS again. So this which one? Tarjan's SCC algorithm also completely works on the DFS and the stack, right? Depth first search and the stack. And Kosaraju's algorithm also works on the DFS and the stack. Just remember this one. This is very important. Kosaraju's algorithm, Tarjan's algorithm. The thing uh, that has to pop up on your mind is this one, DFS, right? First thing is DFS and the stack, right? So then let's do one thing. Let's move on with that. So I just wanted to tell you something. So I didn't find that one relevant. Anyways, so this is fine. DFS and DFN stack, right? So here we have to perform the DFS on the original graph, or we will be performing the DFS on the original graph, and we'll be pushing the nodes onto the stack in the order of their finishing times. Again, we'll be performing the DFS on the original graph, and we'll be pushing the nodes onto the stack after performing the DFS on the original graph. We'll push each node onto the stack in the order of their finishing times, right? So this is fine. Next, transpose and DFS. Transpose in the sense reverse, right? So what we will do here, we will reverse all the edges, right? Nothing but we will be transposing the graph, right? So we have solved transposing the matrix, transposing the other stuff within the lead code and code forces. By this time we have to know the meaning of transpose and other stuff, right? Transpose and DFS in the sense reverse all the edges, right? Reverse all the edges, meaning transpose the graph and perform the DFS in the order defined by the stack. So we will be reversing all the edges, nothing but transposing the graph, and we'll be performing the DFS in the order of this one, in the order defined by the stack. Each DFS traversal in the phase gives one strongly this one connected component. Each DFS traversal in this particular phase gives one strongly connected component, right? So this the same thing, DFS and stack and transpose and DFS, this one will be implementing in the form of code or the algorithm by making use of the Python programming language, right? So why it works? Basically, why it works? The finishing time stack ensures we always start the DFS from the vertices that are guaranteed to reach all the nodes in the strongly connected components in the transposed graph, right? So the finishing time, what it does, finishing time stack ensures we always start the DFS from the vertices that are guaranteed to reach all the nodes, that are guaranteed to reach all the nodes. This part is very important in their strongly connected components in the transposed graph. This is fine, man. The last sentence, this I found this one, I wanted to discuss this one as well. Transposing the graph ensures that the DFS in the phase 2 only explores vertices within the same strongly connected component, right? So this point is very important as well, right? So next, let's do one thing. Let's try to implement whatever we discussed in the explanation. Let's try to implement or articulate the same thing in the form of code, right? Now, first, what we'll be doing. So first thing is Kosaraju's algorithm to find the strongly connected components. So this will be only applicable for the directed graph. Again, Tajan's the SCC algorithm is also applicable only for the directed graph, and Kosaraju's algorithm to find the strongly connected components, it is applicable only to the directed graph. So this one also we have to keep in mind, right? So now let's go with a graph that is represented as the adjacency list here. So I'll just go with graph here. So this one, I'll just go with 0 here. Let me go with 1. This is fine. And 1, let me go with here 2. This is fine. Then let me go with 2 here. 2, from 2, let's go with a 0 as well as the 3. This is fine. From 3, let's go to 4. 8, 4. This is fine. Finally, from 4, 4 is the last one. Let me leave it empty here. It doesn't go from, it doesn't, we don't have edge from 4. Fine. From 3 to 4 is fine. From 4, we don't have any edge. This is fine. Yeah. Now let's move on with the first step, first main step. So we have to perform the DFS and we have to push the finished vertices onto the stack. So that's what we need to do here, right? So I'll just go with def DFS here. So let me pass V vertex. I'll just go with the visited here. This is fine. Let me go with the stack. This is also fine. G. This is fine. Yeah, within that DFS function, let me go with visited of V. So let me set this one to the Boolean value true. Yeah, so we are just marking the current node as visited. Now let's do one thing. We have to visit all the neighbors, right? Let's visit all the neighbors. For that, let's consider the for loop or the iteration part here. This one graph of V, this is fine. If not, if the neighbors are not visited, that particular edge U, right? So then let's perform DFS here. Let me pass. So this is recursive, right? So U visited as well as stack. Let me pass G as well, right? So this is fine. Next, let's do one thing. Let's go with stack dot append. Why this is not showing again? Did I do anything wrong? Hmm, this is fine. We are going with the DFS function. This is fine. This is not showing in the suggestions. Yeah, let me do one thing. Let me pass V here, man. Yeah, this is fine. Not visited of you. I have been corrected for none. If not visited of you, this is also fine. For you in graph of V, this is also fine. Then I hope there is no mistake. This is fine. Let's move on with the next step. Let's go with what is the second step basically? After performing the DFS along with the stack, we have to go with a transpose, right? We have to transpose the graph basically. So I'll just go with def here. Let me go with transpose graph. This is fine. Let me pass G. Yeah. Now, within this function, let me go with gt equals I. This one is fine for I in G. Yeah, we are just initializing the empty graph here. So the next step would be, let's go with the for loop for V in G. This is also fine. Then let me go with for U in G of V. Yeah. Next step would be, let's reverse the direction of the edge. So this one will be gt of U, fine, dot append. So what we need to append here, we are just appending V. So this is fine. The next step is we have to return the gt, right? Transposed graph that is transposed gt. I have kept the variable. So I'll just give here gt. This is fine, man. Now let's move on with the next step. Nothing but let's go with the DFS on the transposed graph. So I'll just go with def here. DFS, this one, let me go with transposed. right? So DFS transpose. So let me go with a V here, visited. So I'll just go with a visited GT as well as, so let me go with component. Just go with component, right? So this is fine. Yeah, DFS transposed. So yeah, this is nothing but the DFS on the transposed graph. So this is here we'll get the transposed graph. Now we are performing the DFS on the transposed graph, right? So this is fine, I believe. So I'll just go with visited of V. Let me set this one to the Boolean value true. Yep. The next step would be here. Why this is showing here? This one screaming here. V is not defined actually. First thing I have defined. Oh, this one. Small v it has to be. Now this is fine, I believe. Yeah. Now let me go with here component dot append. So why this is not showing man again append. It's not showing the suggestions. This is fine. Yep. And now let's do one thing. Let's move on with the iteration. This one has to be for u and graph transposed of u. This one of v, right? Sorry. Now, if not visited of u, then what we need to do? Then let me go with a, let me call DFS transpose here. Nothing but we have to recurse here, right? DFS transposed here. This is fine. Let me pass certain things here. Nothing but v, sorry, u visited graph transposed GT as well as the component. So this is fine, I believe. Yeah, now we are done with this part, man. We are left with one more function, basically the main function, right? So what is the main function here? Kosaraju's, this one, strongly connected component, main Kosaraju function, right? So I'll just go with here def Kosaraju, this one, S double C, right? So this one is G. This is fine. So within the function, Kosaraju function, so what we'll be doing here? First one, let me give visited here. Visited equals, so I, uh, let me go with false here for I and G. This is fine. Let me go with stack. Let me, uh, yeah. Let me initialize this one to the empty array. So this one, let's go with the first phase, nothing but we have to fill the stack with the vertices by finishing time. So let me go with a for loop here for v in, for v in G actually, for v in G. So if not visited of v, then let me give DFS here. Let me give DFS v comma visited. So let me go with stack here. This is fine. Let me go with G, right? So this is fine, man. Yeah, let me do one thing. Let me go with graph transpose that is equivalent to transpose graph of, let me pass G, man. Yeah, this is fine. Now let's do one thing. Let's go with a phase 3. Phase 3 in the sense, let's perform DFS on the transpose graph in the stack order, right? So let me copy or, yeah, we'll be going with the same thing, I believe. So this one will be visited equals I, false for I in G, the same thing, right? So now let me go with what happened here. Yeah, strongly connected components S double C. So this one is double CS, right? So let me go with the empty array. Assign this one to the empty array. So let's go with a while loop here. While of stack. Yeah. So within the while loop, let me assign v2. So we are popping. So let me make use of, we are removing the element, right? Let me make use of the stock dot pop, stock dot stack dot pop. Sorry. So this one, if not visited of v, then what we'll be doing? Let me set the component. So this one component, this one to the empty array. This is fine. Then let me go with DFS transposed actually. V comma visited. This is fine. Comma GT component. This is fine. SCC, strongly connected component. So this one will be, let's append component to the strongly connected component, just double C. Yes, right. So this is fine. Yeah, we're just adding the found strongly connected component to the list in simple terms, right? So this is fine. Finally, what we need to do here, we have to return the SCC as nothing but the strongly connected components. We are finding the strongly connected components itself, right? SCC, right? So this is fine. Now we are done with the algorithm. So this is it for the algorithm, right? So let's run the Kosaraju's algorithm, and I'll just go with here result. So this one has to be the result equals Kosaraju's SCC. This is fine. This is the function. Let me pass graph here. Also, let me print something for the interactive purpose. So I'll just go with, give me a second here, strongly connected components. Yeah, this is fine. Let me pass results here. Result or result. So I have given result itself. This is fine. Yep. Now, yeah. So from 0, we are going to 1. So accordingly with the graph that we have considered, right? So from 1, we are going to 2, right? So this is fine. From 2, we are going to 0, as well as we are going to 3. We are going to 3, right? So this is the adjacency list basically. Now from 3, we are going to 4. From 2, we are going to 3. This is directed graph. So this is applicable to only to the directed graph. Just remember this one. From 3, we are going to 4 actually. Let me give it done this way. Yeah, this is fine. Yep. Now, yeah. So what are the strongly connected components here? Strongly connected components are, first one is 4. This one is strongly connected, right? So this is isolated. So this one is strongly connected. So let me explain this one later actually. Do one thing. Yeah. First one is 4 actually. The second one is here 3. So this one is also strongly connected. Why, you know? Let me explain that one step by step. No worries. And another one is, so see here, this part, this is forming a cycle. You can clearly see here, right? So this part as well. So this one we can just call it as 0, 1, 2 or 0, 2, 1. Yeah, this is fine. So let me call this one 0, 2, 1. This is fine. This is also strongly connected component. So first, why 4 is strongly connected component here? Because see, node 4 has no outgoing edges. So this one, only incoming edge we have here, or yeah, on no outgoing edge at all from the node 4, right? So node 4 has no outgoing edges. So it forms its own strongly connected component. So this is one, the first strongly connected component 4, right? So this is fine. And next we have 3. So this is one of the strongly connected components as well. Why? Node 3 can reach node 4. See here, this one. Node from the node 3 we are going to node 4, right? From the node 3 can reach node 4, but no one reaches 3 back in the transposed graph. So see here, no one reaches 3, this one, 3 back in the transposed graph. So it's a separate strongly connected component, and this one we can connect this one as the second SCC, strongly connected component. Next one is, we have this one, what do we call 0 to 1. 0 to 1, node 0, 1, 2. This one 0 to 1, 1 to 2, and 2 to 0 we have, right? So this one entirely forms a cycle. We know this one. See here, by looking at it, we can say, right? So 0, node 0, 1, 2 forms a cycle. So that is reachable from each other, reachable from each other. So they are one strongly connected component. So this is the third strongly connected component. So the output that we need to get here is 4, this one 4, followed by 3, followed by 0, 1, 2, or 0 to 1. So order doesn't matter. You can just write it on this way, right? 0 to 1 or 0 to 1. So this is the output that we need to get actually, right? I hope this is fine. Yeah. Now let me delete this one entirely, man. I have considered simple, very simple example within the algorithm, right? So let's try to run the code. We have complete understanding of the algorithm. We have performed the DFS, then we transposed the graph, then we performed the DFS on that this one transposed graph actually. Then we went with the main function, nothing but the Kosaraju strongly connected component algo, right? So this is fine, I believe. Now let me do one thing. Let me, sorry, did I delete this one? give control J. Sorry. Yeah, let just give me a second here. My mistake. I pressed this one. Control D. 1 second. Yeah. Let me give control J here. So I'll just give here Python file name dot py. Yeah, so we are getting, see here, strongly connected component 0 to 1, 3 and 4. So we so the order that I went with is 4, 3 as well as the 0 to 1. So order doesn't matter, man. The output is same, right? 0 to 1 as well as 3 and 4, right? So why 4? Again, node 4 has no outgoing edges. It forms its own SWC, strongly connected component. Node 3 can reach node 4, but no one, this one reaches 3 back in the transpose graph. So it's separate. Uh, it's a separate strongly connected component, this one node 3. Then 0 to 1, we saw at the ending. 0 to 1, node 0, 1, 2 forms a cycle, basically reachable from each other. Basically, whenever it forms a cycle, it's a strongly connected component, right? So they are in the, so they are one strongly connected component. So we are getting the desired output, right? So we are done with the Kosaraju's, this one strongly connected component algorithm, right? So we are done with this part, right? So let's move on with the summary part. Let me summarize whatever we have learned so far, right? So just try to remember these 2 to 3 points. First thing is Kosaraju's algorithm efficiently finds all the strongly connected components, right? In Biko of V plus E, in Biko of V plus E, nothing but the vertex plus edges, right? So Kosaraju's algorithm efficiently finds all the SCCS, meaning all the strongly connected components in Biko of V plus E time using the DFS twice, using the DFS twice, right? So this is fine, I believe. Again, Kosaraju's algorithm efficiently finds all the strongly connected components in Biko of V plus E time using the DFS twice, right? So this is fine. So key steps here, uh, basically, first what we'll do, we'll go with the DFS to compute the finishing times, right? The first step is we'll go with the DFS to this one compute finishing times, right? So this is fine. Then what we do, the second step, if you remember, we transpose the graph, right? So we transpose the graph. What is the third step here? The third step is to again perform the DFS in finishing time order to discover the this one strongly connected components, right? So these are the 3 steps. And final step, so this one, sorry, and the final point here, this is one point. So third point or the final point here, so mainly this one, what do we call use cases. So this is very useful. Basically, Kosaraju's algorithm is very useful in problems like cycle detection. This is one of the use cases, cycle detection. uh, and this one, graph condensation, graph condensation as well. And then finally network analysis, right? So network analysis. So these are some of the use cases that I wanted to discuss, right? So this is important as well. So Kosaraju's algorithm is useful in problems like cycle detection. Basically cycle detection, this is basically the cycle is considered as the strongly connected component. This will help in the cycle detection mainly, right? So useful in problems like cycle detection, graph condensation, as well as the network analysis, right? So these are some of the important points I wanted to discuss with you guys, right? So now we are done with the Kosaraju's strongly connected components algorithm, right? So now what we will do, we will move on with the Kahan's algorithm, nothing but the for the topological sorting, right? So next we'll move on with the, or next we'll be discussing about the Kahan's algorithm, right? Also known as topological sorting, right? For now, this is it. Thanks for watching, guys.